welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. Hi everyone, my name is Alice. I'm a host at House of ZK. I'm joined here with Jordi, who's a ZK and Ethereum developer and also the technical lead at Polygon zkEVM. So very excited to have you on here today, Jordi. Very excited to have you.
It's a pleasure to be here.
Yeah, thank you so much. I'm wondering if we can first start off with an introduction of yourself, Jordi. So how did you first get involved in the ZK spaces? And then I'm also wondering about the origin story behind Polygon zkEVM. So what led Polygon to develop its own zkEVM?
Well, my story is I discovered Bitcoin in 2013 or something like that. It was not until 2015 that actually I start discovering Ethereum and getting a lot of involved. At that point, I was involved in the DAO. By that time, I was a white hat there. Also was involved in the parity hack at that point, and was very upset. Very impressed for all the technology and all this new world. It was a kind of a discovery on it was not a new technology, but it's new technology and what you can do with this new technology and the new world that you can create on that. So for me, it was just studying. And I remember at the beginning that appears this thing that was ZK, was Zcash at the beginning. Then remember that in Ethereum, they added these precompiled smart contracts for the Beyond Corp, the pairings thing. So I start studying at this technology and seeing all the power of this technology. At that point, I built what's now zkEVM and SNARK.js. For me, it was a kind of a weekend project to learn ZK. Of course, it took a little bit more than a weekend. Actually, right now, it has been fully rewritten, most of the code and so on. But we're just learning on there. We created Iron 3, and with this zkEVM and all, we were to start doing developing a lot of this technology. At some point, we realized that all this technology, the killer application was the rollups. So we started building what at that point was the Hermes network. And it was just an only payments network, but was one of the first rollups that in the space. And then at that point, we just contact with Polygon and we merged together. Polygon always had the vision to scale Ethereum, to bring Ethereum to the maximum quantity of users, and they bet for the ZK technology. So at that point, Polygon just merged with to buy some projects like us, and the Mir project that now we can Polygon Zero. And that was very much the story, and this is how we get involved to Polygon. Sorry about that. Polygon was was very helpful because we get all the financial and all the incentives just to build the zkEVM. Build the zkEVM in the short time that we built was a huge effort. But we built this zkEVM, the first zkEVM, and I think that we bring the space to a new level, to this new era of rollups and ZK rollups, which is where we are somehow now at this time.
Yeah, nice. And it's really great to hear that you got your start all the way back in 2013 for some Bitcoin, and then you're exploring other kinds of ecosystems and tooling as well. And I think it's so funny that you mentioned that the zkEVM.js was just a weekend project.
Of course, it was just a very reduced version of that. It was a little bit more than a weekend, but it was done really fast. It was more kind of a proof of concept, just to be sure that you understand what really was at that point was Gross 16, or actually it was not Gross 16, it was Pinocchio thing, but yeah, then we proved to Gross 16. But it was, it's super fun. From the developer perspective, when you see a system that's kind of magic and you get deep and you understand how it works, that's quite satisfying for a developer, and it's a nice thing.
Yeah, absolutely. And on the topic of the developer, I wanted to ask you a bit about the developer experience on Polygon zkEVM. And some of the pain points that you see developers currently facing when they're trying to build with zk, and how Polygon zkEVM is making zk more accessible to these developers. I know that you guys have a lot of tooling and support when it comes to, say, Ethereum EIPs and precompiles, as well as different kinds of opcodes as well, making it very compatible to Ethereum. So I'm wondering if you can speak about how the Polygon zkEVM is trying to cater towards having a more optimal developer experience.
I mean, the idea of the zkEVM is not about zk. I mean, it's about the big idea is that you can develop anything like Ethereum using the same EVM and the same solidity and the same tooling and the same precompiles. So if you are an Ethereum developer, you are a zkEVM developer. That's a big thing that you as a developer you get. Other thing is you want to do some zk application, but that's not specific to the zkEVM. That's specific to any chain. I mean, you can use the zk technology as you want. And here, I mean, there is a lot of tooling around zk for building. For building your own circuits. Circom is one example. I mean, Noir is another example. I mean, there is a lot of toolings. I mean, in the case of STARKs, we have Pila STARKs, and we have at this point we have Zisk. If you want to develop zk at this point, for example, all the new zkEVMs here in Polygon, for example, we are developing Zisk. Zisk is a zkEVM. There are others like, I mean, SP1 or RE0. I mean, these are toolings where just you just write a program in Rust, whatever you want to prove, and that's it. I mean, that's very easy from the developer perspective. So, yeah, I mean, this is the future. Of course, the performance of these new systems need to see a little bit less. I mean, it's much practical for the user, but a little less optimal. But it's getting better, and at some point it's going to be that much optimized. The systems are going to be that much optimized for these zkEVMs that they are going to be even faster. So that's probably. I mean, if you are going to develop some zk application, probably looking for some zkEVM platform. It's probably the way to go. If you need to do maybe something simple with for mobile phones, maybe Circom or Noir are the other tooling that probably you need to take a look at.
Mm-hmm. Yeah, and it's very, I think it's very impressive that over the past years we've developed much more tooling and support to make it more accessible to these developers. Now there's different kinds of languages like with Circom, and then also there's even the option to just simply write a program in Rust and then prove it, which wasn't possible before. So very exciting to see kind of this landscape growing over there. I wanted to also ask you a bit more about some of the motivations behind some of the design considerations of Polygon's zkEVM's architecture. So from my understanding, the proving system that you guys use involves both eStark proofs, and then you also have some techniques like Fry that are then compressed into these Flonk proofs. So I'm wondering if you can speak about some of the motivations behind certain design considerations, certain techniques that are being used within the zkEVM.
Well, yeah, I mean, was the big challenge of building a zkEVM was, I mean, the architecture. I mean, choosing the right architecture and the right tooling to build this. Here, very early we realized that the fastest proving system that was, and probably it still is currently in the space, is STARKs. I mean, STARKs and Fry. These are very simple. I mean, everything is based on hashing. Hashing is very fast. zk level. So the minimum, when you have a trace, the minimum thing you need to do something. What's the minimum thing you can do? Is you hash it. Well, that's a Stark, very much. I mean, just super simplifying. Yeah, but that's but the Starks had the problem. I mean, the problem is that if you are trying to verify Starks on chain, this is very expensive, if it's even possible sometimes. So here is where we combine two technologies. We combine the Starks in one side that give us a lot of advantages, proving times, and then we have just as a normal snark, normal plonk. In this case, is Flonk, which gives you the cheapest verification on chain. So, and using recursion, I mean, just proof with another proof. I mean, you are proving that something is proven from a proof. I mean, it's from a SNARK, and then you're just verifying this final proof on chain. You can verify everything. STARKs has another important advantage, which is a little more subtle, but it's important to mention, as that recursion in the STARKs is very, very, very cheap, at least compared to other SNARKs. So that means that you can, with one circuit, you can verify another circuit. So this scales a lot. I mean, because you can have one circuit that proves two circuits, but these two circuits that can prove two more circuits. So you can build a kind of a tree of proofs, and you can condense. I mean, you can put in a single proof something that proves not only a single block. You can prove a full segment of a chain with many blocks on there in a single proof. And this is very, very, very convenient for STARKs. Important to mention also here the usage of small prime fields. In our case, in zkEVM, we are using extensively the Goldilocks. Now there are some projects that start using Baby Bear and Circle Starks. I mean, other even smaller prime fields. But this gives us also a lot of speed up, maybe one order of magnitude of speed up. And this was why it was possible, why it actually is possible to build zkEVMs, something that was something like impossible maybe 5 years ago or 10 years ago. At this point is quite trivial. And I mean, and even going further, I mean, we even have these zkEVMs. This is where everything landed later on. But yeah, but that was the main decisions that we took in the technical side.
Mm-hmm. Yeah, and it's always very fascinating to see how different teams kind of navigates through these through the design space and choosing which types of techniques and tools are most appropriate based on the application that you're trying to build. So very interesting to see all the thinking that goes behind these considerations.
Yeah, and it's also another thing that's important to mention is because here, for example, we are using a STARKs. I mean, the STARKs was invented very much for people from Starware. But we're also using Flonk and Plonk. This was invented by Zach and other teams. I mean, the nice thing of the space is that we are using a lot of tech. I mean, is this knowledge transfer between the projects is continually happen, and a lot of ideas that we have, they are using. I mean, this is a common thing in the open source world and in this community source. Sometimes it's hard, but this is, I think, is a fundamental piece for going faster and for evolving faster. I mean, this openness on the projects and this lack of patents and lack of hidden things. This is amazing, and this is why this world can evolve that fast. So this is something that we cannot lose because this is an important piece for advancing faster in the space.
Yeah, thank you for bringing that up. Definitely, the idea of open source has been very integral to all the developments that are made within the zk space and within other industries as well. We've been seeing so many improvements with reducing proving times, reducing the proving costs, and a lot of it is due to that collaboration that we have. So thank you for bringing that up as well. And then also, when you were explaining some of the major decisions that went behind developing the Polygon zkEVM, you mentioned Stark recursion, which, to my knowledge, use a combination of aggregation, recursion, composition of these proofs. And you spoke a bit about the advantages, like reducing the overall proof size, and then it's also good for compression. But I'm wondering if you can speak about any potential trade-offs that may come with recursion. Are there certain scenarios where recursion should and should not be used?
General recursion is very important when you want to do big things. I mean, when you're doing rollups, you cannot do a monolithic proof. You will need to split the things up at some point. So that's when you are going to need recursion. Maybe if you are in the mobile phone or you want to build a small proof, something very concrete, especially for privacy and things like that, maybe it makes no sense to use recursion. I mean, you would just use a single proof that's proving something very concrete, something that would hide some part of your private data and things like that. if you want to build a proof in a mobile phone, maybe you could use recursion, but maybe it's not a good idea. Maybe it's just do a single proof on that. That's one of the things. But at the moment that you want to aggregate things, that you want to build things, you will need recursion, and this is a really important piece. Probably, I would say that this is one of the hidden key technologies that actually made the zkEVMs possible. This recursion, dominating this recursion, is having full control of this recursion and understanding how this works and putting that in practice has been the big advance.
Got it. So depending on the scenario, like in some scenarios, you may only just need that single monolithic proof, but then in others, you would need kind of an aggregation of those where recursion comes in. Got it. All right, yeah. And I also wanted to ask you a bit more about STARKs, which I know that you contributed a lot to. So I'm wondering if you can speak about some of the main motivations that came with developing the STARK protocol and some of the limitations that were present in air that STARKs helped to address, and some further enhancements, some further improvements that were made on top of just the STARK protocol.
Well, at the end was just taking STARKs. At the end was putting together a lot of other technologies. I mean, taking the technologies that come from Plonk, technologies that come from Flonk, that comes from lookups, and also the way we are generating these STARK when you have that many polynomials or state machines or different layers that they connect one each other. So this is very much the paper of STARK, is how you do that and how you use aggregation also to build these bigger proofs. So the end STARK paper is how we are connecting all these other technologies in order to build efficient STARK on there.
Got it. And then also, from my knowledge, on the ZK prover side, it uses both PIL and then also ZK assembly. So I'm wondering if you can speak about some of the roles that those two components have, and then also the motivations behind developing these two new kinds of languages, and why the Polygon team thought they were needed compared to, say, some other existing languages, other existing ZK DSLs in the space.
Well, Polygon zkEVM was probably the first zkEVM,
right?
Because so it's a VM, it's a processor that's running. So ZK assembly was the assembly of that processor. The difference between the zkEVM processor that we developed for the zkEVM and the current EVMs, RISC-V processors, these are RISC-V, which are much more standard. The processor that we developed was more a specific processor for the EVM in 256 bits with some specific registers in there, with some specific operations that they were tailor-made for the EVM. But at the end was a processor, just a processor. So the assembly was just the language of that processor. We just invented a language for that processor. PIL is another story. PIL is an arithmetization. I mean, PIL is more similar to Circum. I mean, but it's for, instead of working with values, you work with polynomials. Okay, and it's the idea is that it's a language, it's a specific language where you can define these relationships of the polynomials in a very synthetic and very simple way. I mean, the PIL is the arithmetization of the zkEVM. This has less than 500 lines of code, so it's very synthetic. So, and this was also a fundamental piece because, for example, for auditing, that's very much what you need to audit. So it's much easier to audit 500 lines of something that's very concrete and it's doing what it's doing, than maybe just doing a huge Rust code with some libraries that generates some constraints in the fly. I mean, that was really important. I mean, and actually the PIL that we use in the zkEVM right now, we evolved to a PIL2. It's a much more, it's a more advanced language, and on top of that is what we're building this, which is a zkEVM, but more for RISC-V but following the same idea. I mean, it's built on top of PIL2, which is an evolution of PIL, and it's very much for arithmetization.
Got it. And it's it's very great to hear how your team addresses these kinds of trade-offs as well. Because for a lot of, like, say, zkEVMs, they really like the fact that the developers only need to write programs in Rust. But as you said, there's that trade-off, like with PIL, there's only that 500 lines of code. And if that needs to be audited, it's much easier than having, say, thousands and thousands of lines of Rust code that uses different libraries, which adds a lot more to the complexity. So really great to hear how like your approach for navigating with those kinds of trade-offs involved. And then I also wanted to ask you a bit more about the like zkEVM bridge, which I know in my knowledge, in a later iteration is called the LXLY bridge as well. So I'm wondering if you can speak about some of the improvements, some of the enhancements that were made in previous zkEVM bridges and what this new version enables.
Well, the LXLY bridge is the smart contract that allows you to transfer funds not only between the mainnet and the rollup, but also between one rollup and the other rollup. I mean, it's the core of the aggregation layer somehow. And at the end is the idea that's behind the LXLY bridge is a very similar idea that happened at the beginning of Ethereum when they were talking about sharding and how the inter-shard communication. There was some papers around that done by Vitalik in 2015 and so on. So the idea is very much that. I mean, at the end there are trees that are append-only trees, and then you can prove. I mean, you just commit to one tree, all the trees generates a single tree. This tree is broadcast to all the rollups, and then the rollups have a single source of truth, so they can use funds that comes from the other way, from the other side in a specific way. So this has been it's an important piece for that. And maybe the other piece that's very related to that is what we call the pessimistic proof. I mean, one of the ideas of the aggregation layers in Polygon is that each rollup is sovereign by itself. I mean, we are splitting what's the state transition function. So you can have a rollup that has AVM, but another that can have maybe a zkEVM, or another that have a specific application. A specific application chain of whatever. You can have any state transition function, but all of them, in order to commit to the aggregation layer, in order to transfer funds between the aggregation layer, they need to prove what we call the pessimistic proof. And this proof is the minimal thing you need to prove so that the specific rollup is not acting maliciously in respect to the other chain. So even if you have a malicious chain that's doing whatever crazy story inside there, they do not propagate. So whatever is going wrong in that way does not propagate to the other places. I mean, they cannot. And the main idea is that they cannot send. Each chain cannot send much more funds that the chain previously was received before transferring that. And you do that with a single proof. This is very specific. And it's the minimal proof that you need to connect to the aggregation layer. And this proof is very much verifying the integrity of this LXLY bridge. These two things is the core piece of the aggregation layer.
Got it. Yeah, that makes sense. And I wanted to also scope out a bit and ask about your thoughts on the zk landscape as a whole. So compared to when you first started working in this space, what kinds of challenges have recently emerged, or any kinds of challenges at that time that you see that are being addressed now? And what sort of new challenges or new opportunities do you expect we can foresee in the next few years?
Well, at this point, probably the big challenges is these zkEVMs. And we are in a point that it's about scaling this. I mean, it's about zkEVMs. This looks like the end game for writing circuits. If you can write a circuit in Rust, it's done. I don't know if you can do it better. And so the idea is, okay, you write that in Rust, but you want this to go with fast and cheap. Okay, so that's the thing. And this is where the space is working at. In this, we are very focused in Polygon. In Polygon this, we are very focused in building this zkEVM that's very fast in the sense that you can build, you can prove a block maybe in 10 seconds or in less, so it's fast proving, and at the same time costly effective, so you're reducing the amount of money that costs you that. So it's more, at this point, it's about, I would say, scaling engineering. I mean, it's about building things in GPU or even hardware-specific things, and doing the things more economics of getting the economics of scale on that. There is still some margin for the protocol improvements, but I think that we're reaching the, I don't know, maybe there is one order of magnitude, but we are reaching a little bit the end of the optimization at protocol level. I mean, things that you could do it better. I think it's going to be difficult to really improve more from the quantity of computations you need to generate a zk proof. The other thing is, if these computations, we have some hardware specific that we can do it faster and cheaper. But we are already in this, I would say that we are in this last phase on the zk era on that.
Got it. So on the protocol level, we're like nearly there in terms of the optimizations, and there's some new opportunities that we can see with further accelerating.
There's still some margin, but I don't think it's a lot of margin remaining.
Got it. Yeah. And now that we're like basically nearly there, I can imagine that there would be a number of use cases that are enabled as well. So I'm wondering if you can speak about some of the use cases within zk that you are personally very excited about, or you would like to see being built more in the future.
Well, I mean, probably maybe the first example that comes to my mind is the bean chain and the evolution of Ethereum. I think this is, I mean, it's they call it this way. I mean, it's a zk consensus. So using zk for consensus is definitely one of the interesting things that's going on. Of course, all the rollups, app chains, and this is going to be another topic of evolution. But then there is other places where I think it's important, things like privacy, applications related to privacy, or applications that are more related to identity or proving things in real world that are going to be interesting. I mean, these privacy things. Still other applications more specific like voting and other, but it's I mean, zk, it's huge. I mean, if you can use it for many applications, especially the privacy ones, which, I mean, contradictory were the less. So zk evolved not for the privacy, evolved more for the scalability, but where probably there are more applications in zk is in the privacy side.
Right, and it's very exciting to see kind of the breadth of these different kinds of use cases, both on the Ethereum side, like with Beam Chain, but then also even for those beyond Web3, like what you mentioned on the privacy side, applications like with voting. So it's very exciting to see kind of like the breadth of all of these use cases that can be enabled. So we're in a very exciting time.
Definitely.
Yeah, absolutely. And thank you so much, Jordi, for joining us on our House of zk podcast. Yeah, I really enjoyed hearing all the developments that are currently being made with Polygon zkEVM, and then some of the kind of thinking behind the design considerations, and then also your general thoughts about the zk landscape as well. So appreciate all the insights from today.
Thank you very much for having me.
Yeah, thank you so much.